Hello, my name is Antonio and I'm presenting BitFun. Nowadays, we are experiencing a rapid growth of geospatial array volumes. Geospatial arrays originate from satellites, numerical simulation UFs, and other sources. For example, Digital Globe, a commercial company, alone acquires about 80 terabytes per day of satellite imagery. DBMS manage large ND arrays, time series, weather-focused satellite imagery, and other ND arrays. Let us take a query example with a tunable function. As input, we take two large 2D arrays storing intensities of reflected solar radiation near infrared spectrum and red spectrum. As output, we get a large 2D array, SAVI, soil-adjusted vegetation index, which aims to minimize soil brightness influences. It is special because it includes a tunable parameter whose value is not known in advance. We may tune L many times to find an appropriate value. In practice, SAVI can be used to predict crop yield according to the recent publication. However, we need to recalculate the crop yield each time we tune L. SAVI is not alone. Dozens of math functions with tunable parameters are used in practice. Currently, array DBMSs answer queries with tunable functions as follows. For the first query, we get some L value and compute SAVI from scratch. Next, we slightly tune L and submit SAVI query again with the new L value. However, SAVI is again computed from scratch. This repeats for each subsequent query regardless of whether we computed SAVI before or not. In contrast, BitFun works as follows. During the first query, BitFun computes SAVI from scratch and indexes the SAVI function. During the second query, BitFun doesn't compute SAVI from scratch. Instead, BitFun uses the index to answer the query. BitFun tackles an important class of queries not explicitly considered before in the context of array DBMS, tunable queries. BitFun explicitly focuses on the fact of tunability. The BitFun approach from a bird's eye view looks as follows. The BitFun index contains identifiers of simpler functions approximating the given function with the required precision. Real data is not random, so the number of approximating functions is typically small, and the indexes have good compression ratios. BitFun can answer three query types, namely compute function values, evaluate inequality, and perform classification. BitFun is integrated into ChronosDB, novel file-based distributed geospatial array DBMS. Now let's look at the BitFun web interface. It consists of several parts. First of all, it has the link to the BitFun homepage, the link to the fascinating BitFun lessons which are encouraged to take, editable box with ChronosDB commands which you can modify and run any ChronosDB command, interactive web map, tune facilities, and ChronosDB output. To obtain SAVI, we need two input arrays, red and near infrared, band 4 and band 5 according to the Lancet 8 band designations. So let's first discover band 4 array and then band 5 array. So in order to obtain SAVI index, we need to run the cal command. We assign near and red synonyms to band 5 and band 4 arrays respectively. The output is the SAVI dataset. The function is SAVI. The tunable parameter is L, ranging from 0 to 1 with step 0.01 with a start value 0.8 and precision 0.1. The output data type for a SAVI is float32. We can optionally compress our index. Due to time constraints, I already ran this command and obtain SAVI. So let's just discover SAVI and visualize SAVI using the WMTS protocol standardized by the Open Geospatial Consortium and implemented by ChronosDB. So I will add SAVI to my interactive matters. As you can see the difference in colors because Lancet 8 scenes were required a different date. So you can use a tune command, WMTS tune command to tune L value and recompute SAVI, or you can just use the tune slider. For example, you can set 1 value to L and you see it of the interactive map. The colors reflect that the L value was changed and the SAVI was recomputed. You can explore the scheme of the SAVI array as it is a usual ChronosDB array. It's a large array covering part of Europe, but its format is the BitFun index format, so you can compare with an ordinary other input array of ChronosDB and find out that their sizes are equivalent. However, the volume of the SAVI index is 10 times less than the volume of input band 4 and band 5 arrays. You can find more about BitFun from the BitFun homepage and its paper. Thank you.